Okay, let's look at problem 3. In this case, we have a JK flip-flop, and both the inputs J and K are basically tied to 1, right? The flip-flop is a edge-triggered flip-flop. We know that because there's a triangle at the clock, and uh, and it's a positive edge-triggered flip-flop because there's no bubble there. Okay, so how does a JK flip-flop work? Do you remember that? So let's J K, and let's write Qn plus 1. Okay, so how does JK flip-flop work? If J and K are 0 and 0, the output is going to remain the same as the previous input. If J is 1 and K is 0, then you have Q equal to 1. If J is 0 and K is 1, you have an output equal to 0. And if J and K are 1 1, then you have an inversion of the state, right? And of course, all this happens at the clock transitions. So I've not drawn the clock here, but so it's a shortened version of the truth table here. Okay. Now what we have is we have J equal to 1 and K equal to 1. We have fixed both of those, which means that we will be only operating in this particular stage and nothing else, right? So what we are going to have is when the clock comes, your output is going to invert. Okay, otherwise the output is just going to remain the same. um, so so if you then want to write the truth table, you could write it like this, right? You can put the clock in. You can say when there is no clock, your Qn plus 1 is going to remain the same as Qn, and if there is a positive edge of the clock, your Qn plus 1 is going to become Qn bar. And that's how this circuit works, and we can stop at that. I mean, if you want, you could draw the signals out, but I think this is fairly clear.